don't know if there's any way to adjust that.
There's some button on the document. It says iris or something.
Iris, ah. Keep going. Okay, so the construction that we've been working with, just keep reiterating the basic data of a compact abelian group, a representation of that compact abelian group on Cn acting diagonally, and then a G-invariant polynomial W. And this data leads under certain conditions to physical theories which are closely associated to Calabi-Yau manifolds. And a typical sort of thing, example one that we've been working with so far, has been G equal U1. You can specify the U1 action by saying what exponents will be used on the generator of U1 when acting on the various variables. And then a typical polynomial that we've used is x0 times a homogeneous quintic polynomial in x1 through x5. So that's been the main example that I've used so far in these lectures. I also want to have at my disposal today example 2. So in example 2, we'll use U1 squared as the group. We'll have 7 rather than 6 homogeneous coordinates, and they're not all quite the same. Let me just mention where this example is going to come from. It's going to come from blowing up the singular locus of a weighted projective space, P11222, which is singular along x1 equals x2 equals 0, and the x6 is a new homogeneous coordinate which gets introduced during the blowup. So this is one of the so-called two-parameter models that Philip has referred to it as the octic model. It sort of plays a common theme in a lot of the literature. Lots of people have done explicit calculations with this example, and so there's a lot of nice things to refer to if you're trying to study what goes on in general with questions like these instanton sums and moduli. So here is the group data, and then again, the type of polynomial that I want to take is going to be of the form x0 times a polynomial in x1 through x6, and I'll just say G-invariant under those conditions. So you need to put in, so the polynomial is going to be of even degree in x1 and x2, and you need to put in half of that degree, whatever it is, in x6 to compensate, and then we want to make sure that it has degree 4 in these variables because of the x0 term there. So that actually determines a finite collection of monomials, and it's another pretty common example. Just as in the example number 1, what happens when you do that low energy analysis is you first get restricted to x0 equals 0, and then you get restricted to the 0 locus of this polynomial somehow sitting inside of that weighted projective space, or the blow-up, I should say, of that weighted projective space. So the analysis of that group action really depends on the location of R. So remember that R is supposed to be in the dual of the Lie algebra of this compact group. And the way that ends up playing a role, so we couldn't see that quite so explicitly in the original one-parameter example, but now that we have 2 parameters in example number 2, what one finds is that there are various regions in R1, R2 space with the property that the topology of mu inverse R mod G, and also the set of possible coordinate charts that you would use to cover this, these things are constant within the regions. And there are various ways of attacking the problem of combinatorially determining which regions we might have. So the essential point is to write down expressions such as R1, which you can see from the group action over here. R1 is minus 4 x0 squared plus x3 squared plus x4 squared plus x5 squared plus x6 squared. So that tells you that there are different behaviors of the group of variables x3 through x6 and x0, depending on whether R1 is positive or negative. So, sorry, my region isn't actually one of the regions. It's just meant to illustrate that we'll divide the space into regions, and the basic division into regions comes about through an analysis of this group action and of the various things that can happen for linear combinations of the R1 and R2 in which different subsets of the variables have different signs, and possibly some subsets won't occur in the linear combination at all. From that, you can do a sort of detailed combinatorial analysis, and what you produce is this same construction that has occurred in Bhattarav's lectures, the secondary fan associated to this data. That so-called secondary fan is the fan structure, the structure of decomposition into regions on G star, which is determined in this way. So that's an important part of analyzing these models, understanding the combinatorics of the models. I think I'm now deciding this is not the best pen to be using. If anybody has a nice, thin felt tip pen that I could use, maybe I'd switch to that, since the pen we were using before disappeared. Yeah, thanks. Great. I think that'll be hopefully that'll be a stronger line. Okay, so within one of those regions, we'll find, within various of those different regions, we'll find different ways of describing, different topologies of the ultimate toric variety that we get. And there's another way of describing the toric variety, which is also constant through the region, and that is to describe it using the complexification of the group that we've been discussing so far. So it turns out that there is some subset of Cn, which I'm going to call script Z of R, which you can remove from Cn in such a way that the space we've been discussing, the mu inverse of R mod G, is isomorphic in some natural sense, to a quotient by the complex group of Cn minus a certain subset. Z of R turns out to be a union of some subsets for I in some collection of indices. So I've got to take each I to be a subset of I1 to In, and I take I take the intersection, of the set where X, this is intersection of I and I, set where Xi is equal to 0. So we take there are various subsets which are going to be determined somehow by this data. I'll explain how in just a moment. We take the common zero locus in Cn of setting those particular homogeneous coordinates equal to 0, and then we take the union over a certain finite collection of these things, and that's how we determine ZR. This is actually very closely related to the analysis that we've discussed before of how to work out which coordinate charts belong to mu inverse R for a particular value of R. So the actual sets that we use, so I is in I of R, should have been I of R, if and only if Xi, the set of Xi for I in I is not a subset of a coordinate chart, the coordinates in the coordinate chart, in any coordinate chart, which is used in this model. So the way that I had discussed of addressing this yesterday was to study the effect of the group action on the complementary set of coordinates, and here we see that there's another way of describing the same group quotient, just removing the zeros of certain collections of homogeneous coordinates and then taking a quotient by the complex group, and you produce exactly the same space. It's perhaps a little harder to analyze because the orbits of this GC can vary in dimension. You have to be a little bit careful about what that means. But by removing an explicit zero locus like that, there turns out to be no ambiguity about the quotient. There are no orbits that have closures that lead to ambiguity in that quotient construction, and we get another description, an alternate description of the toric variety that we're looking at. Okay, so armed with this, we're actually in a position to be more explicit about the structure of the instanton moduli spaces. But before I go back and get explicit about the structure of the instanton moduli spaces, I want to return to one additional feature from the physics, which I promised you a couple of lectures ago, which is a so-called one-loop correction in the case that a singularity is developing in the physical theory. And this one-loop correction will completely determine the location of the singular locus. So remember, we have two sets of parameters here. We have the parameters which we've labeled as tau. Those are supposed to be, these are parameters really corresponding to homomorphism from the group into the complex numbers. And then we have parameters which are the coefficients of W. And most of the physical effects that I'm going to be discussing are completely insensitive to changes in the coefficients of W. So these are really not relevant to the current discussion. What's relevant to the current discussion are these parameters which just look like homomorphisms from the Lie algebra G into the complex numbers. Well, when I discuss a singular locus, I'm actually talking about values of the parameters at which the physical theory acquires some kind of singularity, doesn't make sense for some reason or another, and that's going to correspond under mirror symmetry to a much more familiar construction where the singularities of some mirror Calabi-Yau manifold are actually causing the singular locus to occur here. And it's really quite remarkable that the physical calculation whose results I'm about to describe ends up leading to precisely the same singular locus. So if we want to identify the singular locus, going back to the physics, we had what was called the potential energy for the bosonic fields, the bosonic potential. And I wrote out for you two parts of that bosonic potential before. There's some constant which normalizes it, but I had these terms dA squared, which had the R in them, and we used to, it was the solving of this particular term being set equal to 0, which led us to the mu inverse of R mod G description of the toric varieties. And then we've imposed these conditions, and we've seen that those conditions end up leading us to a compact subspace within the non-compact toric variety, and then further restricting us to the zeros of some polynomial, like the quintic polynomial. But there was a third term, which I didn't write for you the first time that this came up, and that third term involves, so I'm writing it with respect to choice of basis. So this is with respect to a basis V sub A of the gauge fields. So remember that the gauge fields were supposed to be a map from the Minkowski space or the Minkowski superspace, this gauge multiplet, into the Lie algebra. So I've just chosen a basis essentially of the Lie algebra to discuss this thing. Each of those gauge fields had a field strength by taking two of these superderivatives, and then the field sigma A is the lowest component, sigma sub A restricted to the body of Minkowski space M sub 2. So those were some of the fields which occurred in the physical theory when we discussed the physical theory the other day, and there's an additional term in the bosonic potential that looks like this. Now, this is a Hermitian form on the space of possible values of sigma. And for generic values of the phi's, or I should say, in fact, of the parameters in the theory, so the values of phi's are determined by the parameters through this moment map construction, right? Mu inverse of R mod G. For generic values of the phi's, we get a positive definite Hermitian matrix, or Hermitian form, I should say, on the space of sigmas from this formula. And so to minimize it, in that case, sigma A must be 0. All the sigma A's must vanish in order to minimize a positive definite Hermitian form. But for some special values of the parameters, the Hermitian form may become only positive semi-definite. And if it's become positive semi-definite, then there are going to be possible allowed values of the sigma A's which aren't 0 and which will affect the conclusions that we've made about the structure of the physical theory. So really there was an implicit assumption already in the earlier analysis of the physical theory that these sigma A's we could set equal to 0. I didn't mention that, but that was part of knowing that we were done with this analysis. And when the sigma A's are not equal to 0, other things happen in the physics that we now have to try to discuss and account for. Well, since this isn't really a course about the physics, I'm simply going to tell you the phrase of what you do. So there's a divergence in the physical theory, and this divergence is regulated with a cutoff. And when you go through this mysterious process, you have some divergent integral, which you write down, but you, instead of deciding to integrate it all the way out to infinity where it would diverge, you only integrate it out to some finite amount, and then you calculate from that some kind of effective description of the theory in the sigmas. And out of that effective description in the theory, you draw a conclusion about the parameter values. So I'm going to write that conclusion in, well, the way it would originally be written is that the parameter values, that this can only happen if the parameter values satisfy a certain slightly complicated looking condition. So I have to write QIA. Again, I'm using my basis. The QIAs are the exponents that occur in the group action with respect to this basis. QIA times log of the sum of all the QIB sigma b's. And this is summed on I. And this kind of Q log Q type term is a fairly common thing to see in this maneuver in physics. These are called one-loop corrections. And these one-loop corrections locate the possible parameter values at which these sigmas might have this kind of problem. So we definitely find singularities there. Those are singularities in some sense associated to the entire group G. And there can also be singularities associated to subgroups G prime of G, where you would restrict somehow to an expression like this that was calculated over the subgroup. Well, I don't have the time, and you don't have the background for me to be very explicit about this, but let me just show you what happens with this little computation in the two examples that we're studying. In example number 1, so it's maybe, actually before I do that, it's maybe nice to exponentiate this. E to the 2 pi I tau, that's the thing that we'll call QA eventually. That QA parameter, if I exponentiate here, looks like a product from I equal 1 to n of terms that are the sum of QIB sigma b raised to the QIA power. So in example 1, we've got x0, x1 through x5. We've got powers like this. There's a single sigma, so I won't put an index on it. And this prescription says that I'm supposed to take, well, minus 5 sigma to the minus 5 times sigma to the 1 times sigma to the 1 times sigma to the 1. There are 5 of those. And that's supposed to be the value of Q at which there is potentially a problem. So I've just read off what that formula says in this particular case of example 1. And now if you look at that, the sigmas cancel out. And the answer is minus 5 to the minus 5. So this one-loop method for making a calculation predicts a singularity of the physics at Q equals minus 5 to the minus 5. On the other hand, last time we actually worked out what the correlation function was in this example. And the correlation function looked like phi divided by 1 plus 5 to the 5th Q. And that was from summing that Instanton series. And indeed, that's exactly singular at Q equal minus 5 to the minus 5. So, well, I don't know how convincing it is. It's powers of 5, which seems to be a theme for the quintic example. And particularly since I haven't told you what the origin of this formula was, maybe it's a little too convenient, perhaps, the way I've written it down. So let's work out what it says in example 2. So in example 2, as I mentioned, there are subgroups to worry about. So the computation actually has to be done twice. It has to be done for all of G. So I'll remind you once again what the charges are in example 2. So they're minus 4, 0, 0, 1, 1, 1, 1, and then 0, 1, 1, 0, 0, 0, minus 2. So when looking at the entire group G and reading off what this formula says, well, there are 2 sigmas to worry about now, sigma 1 and sigma 2. So the first term, that this sum of the charges times the sigmas looks like minus 4 sigma 1, and if I'm reading across what it says about Q1, that's to the minus 4 power. The next 2 are to the 0 power, so I won't include them. Then I've got sigma 1 to the 1, sigma 1 to the 1, sigma 1 to the 1, and sigma 1 to the 1. Excuse me, that last one was wrong. Sigma 1 minus 2 sigma 2 to the 1. It also says that Q2 should be given by, well, this minus 4 sigma 1 is raised to the 0 power this time. I'll leave that out. Sigma 2 to the 1, sigma 2 to the 1. And then the last one, sigma 1 minus 2 sigma 2 to the minus 2. So it's a fun exercise to figure out what happens. These are homogeneous of degree 0 in, total degree 0 in the sigmas, the same thing that happened over here. And so we'll actually be able to solve for the ratio in this particular case, eliminate it, and get an equation between Q1 and Q2. A reasonably efficient way to do so is to write Q1 as minus 4 to the minus 4. That's just taking care of this 4 power. And then if you look, I've got 3 powers of sigma, a negative 4 power of sigma, and this expression. So that looks like sigma 1 minus 2 sigma 2 over sigma 1. So if I decide that sigma 2 over sigma 1 is the quantity that I'm interested in, I've got minus 4 to the minus 4 times 1 minus 2 sigma 2 over sigma 1. Q2, similar way of thinking about Q2, is sigma 2 squared divided by sigma 1 minus 2 sigma 2 quantity squared. So that, in terms of sigma 2 over sigma 1, is sigma 2 over sigma 1 squared divided by 1 minus 2 sigma 2 over sigma 1 quantity squared. Yeah, it's maybe slightly tedious elementary algebra to finish this, but